Let's see. This would be limit delta x approaches 0. Oh, wow. What a mess we have here. The temptation is to say, we'll use the conjugate, right? I know some of you are saying that. Let's just use the conjugate. Let's multiply both numerator and denominator by this quantity plus that quantity. But we've got a problem with that. We've got a problem. The problem is that, let's just do this way. If I have the fifth root of a, we'll make it simple here, minus the fifth root of b, and I try to use the conjugate of that, we use the conjugate to do what? To make the numerator rational, which means we don't have any more radicals in it. But if I multiply those together, I get the fifth root of a squared. If I multiply these, I get minus the fifth root of b squared. Have I really taken away the rationals, the radicals? No. So we got to be real careful. The tendency is that whenever we see a radical and we're just going to use the conjugate, it doesn't always work that way. We'd have to do something else, and that something else would be so long and time-consuming that we've got to figure out another way of doing this. Okay, so we can't use the conjugate. What we can do is let's go back and let's use the alternate format. This is one of those cases I was telling you where we want to use the alternate format or process, I guess we were calling it, alternate process. Okay, nothing wrong with our approach, but with the tools that we have, we really don't want to get into this work. Okay, so let's start over again. And now let's go back and let our graph help us. And we said that something seems to happen at x equaling 0. Let's try that and see. Let's see what happens here. So let's take the derivative at 0 as the limit as x approaches 0. Remember that alternate format? It will be f of x minus f of 0 divided by x minus 0. Well, let's see. F of x is the fifth root of x squared minus the fifth root of, we could have done that in our head, but I'll put it down anyway, divided by x. Can you just let me use x there, now that we know x minus 0? So we've got the limit as x approaches 0 of x to the 2/5 power divided by x. And again, all we have to remember is how do we divide using the same base. So, this would be 5/5. So, 5/5 minus 2/5 is 1 divided by x to the 3/5. I don't care what that exponent is because I've got a problem. Does not it's undefined. The limit does not exist. Now, would it make a difference if I came into this from the less than 0 side or the greater than 0 side? No. Okay? It does not exist. What's happening? Well, usually, again, when you divide by 0, what you end up with is an asymptote. That's not necessarily the case here, although we are having it, the derivatives, and again, if we were to put points on either side of this and we find the tangents and find the slopes of the tangents, we'd find that these tangents are going to be going very, very negative on this side. And on this side, they're going positive, more and more positive. And so we have that. And I'll just let you use that word if you want to. The cusp, that means a very sharp point. So do we have a derivative? Now, did we answer the question, though? That's the next big thing. What's it say? Describe the input where it is differentiable. So, f of x is differentiable. I'll give you one more answer, John K. For what? For all reals, as long as we don't use 0. Okay, yeah, all reals as long as we don't use 0. Okay, one last slide, and then we're done with these notes, and we'll get on to handing out some papers and looking at a real short review here. Yes? Is that what? Yeah, it's the name. It's the name of that sharp turn that happens in curves. Okay? It's just the name of it. Okay? So, now, the idea here is we have 3 ways that a derivative fails to exist. We found one. We can, you know, if you don't want to, if you get the name of it, just remember that there's a sharp turn. Very sharp turn. We also found out, what was that theorem? Differentiability implies continuity, but we also found out then, we talked about how if it's not continuous, there is no derivative. Okay? So it has to be continuous. And the last one we haven't really talked about, but it is possible to get a vertical tangent. Now that vertical tangent is going to come primarily with a function that's something like this, the cube root of x. And remember, the cube root is the inverse function of the cube. And so it looks something like this. It's like taking that cube and doing something like that. And believe it or not, at this point, you get a vertical tangent here. I didn't draw that as cleanly as I should, but at this point you get a vertical tangent. We don't have a lot of those that come up, but they do come up occasionally, so we need to know. And what we end up with is that, well, it's just vertical, which means that it's infinity. It's very, very infinite at that point. Okay, well that is all of the notes I have for you. So when you prepare for this, don't forget 3.1's on the test Tuesday. Also, don't forget that you need to go back and look at all of the lecture notes and be able to read of the